Hi students, welcome back to class or this lecture here. This lecture is going to be about some ocean characteristics to get us started in the marine carbon cycle part of or the module. So first of all, I just want to recall or remember the fact that the deep ocean is going to be a very large reservoir for carbon. Um, it is going to be a net sink. The things that will sink the carbon will be, the deep ocean, and then some carbon will get into the ground through subduction. Um, so there's definitely a large store of carbon within the ocean. It is the second largest reservoir. Um, so just to kind of go into the oceans here, most of the time you learn that there's four oceans, and most, at least I learned it when I was in school, there's four oceans. But oceanographers do consider the Southern Ocean or a fifth ocean here. The reason why is because there's a circulation that goes around the Southern Ocean like this, or I'm sorry, the Antarctica like this in the Southern Ocean, and there's going to be some like ridges on the edge of it, and it's going to make it real difficult for that circulation to change. So there's going to be some, characteristics that'll be unique to the Southern Ocean, and it's really hard for water, for that circulation to really deviate from that system there. So another thing to kind of go into here is that, traditionally scientists have studied the Atlantic and the Pacific more than the other oceans. And the reason why is simply it was just more accessible. So, settlers and people that were, measuring ocean temperature and measuring these types of things, they were generally speaking over here in Europe and then on the East Coast and the West Coast of the United States. So this resulted in a lot more studies done in the Atlantic and the Pacific, and we have a lot more records on those two oceans than we do in the Arctic and the Indian. Now, the Arctic is definitely important to climatologists, through albedo feedbacks, the circulation, which we'll go through here in a minute. The Indian Ocean is also really important, especially to meteorologists, because more regional type of weather systems are attached to the Indian Ocean. But, I just wanted to kind of let you guys know that the Atlantic and the Pacific here, they're definitely a lot more studied. Um, okay, so I kind of mentioned through the circulation, which we will go over here in a minute, and that circulation that I was speaking of is the thermohaline circulation. This is the circulation or the conveyor belt that goes around the whole globe. It is kind of I want to say two roots that are put together. So thermo meaning temperature, and then haline meaning salt. So you put it together, this is going to be the major ocean circulation patterns driven by the density of the water. So the density is controlled by temperature and salinity, or the salt content, if you haven't heard the word salinity before. So cold water is going to be more dense, and therefore it will sink, and hot water is going to be less dense, and therefore it will rise to the surface, kind of just like in the atmosphere. And then, water that has a higher salinity or a higher amount of salt in it is also going to be more dense. And so, therefore, that is actually going to fall. And then, if it's less dense or has less salt, then that would actually rise. So, this is going to be the basics of this thermohaline circulation. But before we talk about the circulation, let's talk about the structure of the ocean a little bit. So the first piece of it is going to be the surface zone. And now the surface ocean, or the mixed layer, some people call it the mixed layer, I've heard that as well. This is actually affected by the winds, okay? So when we're talking about this, understand that the surface zone is affected by the winds, but the other two areas will be affected by other things. So we'll talk about that here in a minute, but I just want to stay on the surface right now. This is going to be characterized by when light can penetrate, so it can sometimes be called the euphoric zone, euphotic zone. This is also where photosynthesis takes place. This is a small part of the ocean as a whole. It's only 2% of the ocean. All right. And then why isn't it always the same depth? The reason why it isn't always the same depth is because, well, let me go over here, that this is going to be increasing latitude. So this is going to be like the equator, and then this would be the North Pole, and then this is the depth. So you can see that it kind of stays down closer to the equator. And so, and it's, it's not really going to be, or it's not even present here at the North Pole. So the reason why it's going to be different depths is because of storms. So there's going to be more storms and more winds closer to the equator, which is going to bring it to be deeper. Okay, so the second layer of the ocean is going to be the pycnocline. Pycno is another word for density, so that's where they got the name from here. You may also hear it referred to as the thermocline or the halocline, depending if we're talking about the temperature or the density. So this is going to be an area where the density of the water, there's like a gradient in that density. So, and remember that density is going to be affected by temperature or salinity. Now, this actually it only is 18% of the ocean. So again, these are very small, and you can see from this picture here that it's not a very large chunk of the ocean. It's a very small one. The major part of the ocean, or the largest part, is going to be this deep zone. This is going to be 80% of the ocean water. So this is going to be the coldest and the most dense water, which makes the most sense because we said that cold, dense water was going to sink down towards the bottom. So it makes sense that the coldest and the densest would be towards the bottom. And this actually, has a fairly constant temperature and density. You're not going to see a gradient here. I mean, you'll see some changes depending on where you go, but generally speaking, we can say that it's fairly constant. It doesn't really change very much. Okay, so to kind of get into some data here, just to kind of look at something, we're going to look at this, which is a cross section. You can see right here, I don't know how big it is, kind of small on my screen, but you can see right here it's going to be 60 degrees south, and then it's going, here's the equator, and then it's going to go up to 60 degrees north. It's right here in the Pacific Ocean. So, let's kind of go over where the mixed layer and the thermocline and the deep ocean is. So you can see that there's definitely going to be, well, actually, let me just explain. This is also the bottom of the ocean here, where you can see that there's going to be some kind of hills and valleys there underneath the water. You can also see right up here, this is definitely the warmest water. So this warmest water here in the reds, this is going to be where the mixed layer is. This is going to be the topmost part. Makes the most sense, right? Because it's going to be what receives the radiation from the sun. It's going to warm it up, so it's going to be warmer up here. Now the thermocline, remember, this is going to be the one characterized by a temperature gradient. So what we're going to see is something from about this like orange right here, right about there, right here to this lighter blue. This area right there is going to be what we would consider the thermocline. Now the rest, basically about 2,000 meters and down, this is going to be all deep ocean. So this is going to be your coldest water, your most dense water, those types of things here. Okay. All right, so now we're going to look at salinity. Again, this is going to be the bottom of the ocean here. You can see 60 degrees south. This is going to be the equator. This is going to be north. This is going to be the depth. Okay, so you can see that this boxed area here is more salt. It's more salty. This is our scale here. So this is me down here is less salty, and up here it'd be more salty. So you can see these red areas right here are going to be more salty. So I want you guys to think kind of why that might be salty right here. So it's actually saltier here because of evaporation. So this is going to be closer to the equator, right? So we're going to have a lot more sun that reaches this, the surface of the water here, and is going to evaporate, leaving behind saltier water. But why is it going to be less salty over here, closer towards that North Pole? Now that's actually going to be from melting of ice and snow, things like that. You're introducing at that point fresh water into the salt water, which then means it is going to be less salty here at the pole. You can see here at the South Pole, there's not as much going on, and it's because of that circulation that's going around that South Pole. So it kind of protects it, so it's not, it's not melting at such a rate as the North Pole is. All right, so this is going to be the Atlantic. This is the same type of thing, same cross section. It's just made the Atlantic instead of the Pacific. So I do kind of want to point out a couple things to you. You can see right here that this is going to be some cold water. This is sinking near Greenland. It's driving deep ocean circulation, right? So we have this cold water that's going to be more dense, because obviously it's colder up there, and so it's going to sink down towards the bottom of the ocean, and then it's going to start driving the circulation that goes around the whole world. You can see also that this is going to be cold water from the Southern Ocean. This is really cold. The Southern Ocean is really, really cold. So you can see that that is kind of sinking down into the ocean right here. All right, so the conveyor belt. This is going to be where deep water rises to the surface in the North Pacific and cold, salty water sinks in the North Atlantic. So remember, this is the United States here, okay? So this is actually the Pacific Ocean, and then this is going to be the Atlantic Ocean. Okay, so like we said, cold, salty water sinks in the North Atlantic. So right here, we'll just kind of start here. It sinks down, and it starts its journey. Now, it can either go over here into the Indian Ocean and then move closer up to the surface. See, it's at the equator, so it warms that water up. Okay, so it goes closer up towards that surface, and then it may go, back over the Atlantic, or it might go, it's going to go that way, sorry. But also, it might go and get caught in that circulation of the Southern Ocean. That's another thing that might happen to it. Or it could also go to the Pacific Ocean. Okay, and take its truck over here, and then kind of rise here in the middle, and then come down here. Now, I don't want to confuse you guys with the gyres. If you're familiar with that, don't get too confused. Like you can't really see it in this picture, but like over here, would be the Gulf Stream. There's a California current. These things are closer towards the surface. This is towards the surface here. But this is not the same as the gyres that we have in the ocean, so I don't want to confuse you guys with those two things. But why is this important to us? Okay, this is important to us, number one, because of the memory, okay, of the ocean. So what I mean by that is that anything that it takes down into the ocean with it, like carbon, is going to be down there for 1,000 years, and then that carbon that gets caught in the circulation is just going to come back up in 1,000 years. Okay, so it's not like it's down there forever and it's never going to come back up. I mean, we already know it'll take a while, and we have reservoirs and that kind of thing. But I mean, like, if it's in the circulation and we put that carbon in today and then say, we become carbon neutral in the future, then, 1,000 years from now, we're going to start seeing carbon coming back up due to the circulation or outgassing from the ocean. So that is everything I have for you guys for this week. I'll see you guys next week. I hope you guys have a great day. Thanks.